Welcome. Today we will see how to use ILD concept for finding maximum bending moment at a section when there is shorter UDL, what you see it here. Shorter in the sense the span of the load is 6 meters, whereas span of the beam is 30 meters. So the load span is smaller or shorter compared to the span AB of the girder or the beam. Okay. So my interest is what is maximum bending moment at this section which I have chosen. So I have chosen a section of 10 meters. So you have seen in my previous video lectures that how to plot ILD for bending moment at a section. So this is what I have drawn, the ILD for bending moment. Okay, this is the ILD which I have plotted for bending moment at C. Now the question is, for what position of this UDL the bending moment at this point or the section C will be maximum. Okay, so for this the load has to satisfy a condition for it to be placed. What is that condition? So you might have learned that the section that you have taken, okay, what ratio it is dividing the span. You see it is 10 by 20 is the ratio that the section is dividing this span, right? So left span is 10, right span is 20. So this is the ratio in which it is dividing the span. So the load shall also be divided in the same ratio. Okay, so that is the condition for getting maximum bending moment at a section. So I'll place this load now randomly. I don't know where exactly it is to be placed. Okay, so I'll keep some load onto the left of the section, that is say x, and remaining will become 6 minus x. Okay, so this is how I shall place the load. Now you see the ratio of the load divided by the section. Okay, so that you need to find 6 minus x, right? So it will be 10 times 6 minus x is 20x, cross multiplication. Then it will be 60 minus 10x here, right hand side 20x. So 60 is equal to, this goes to the right hand side, become 30x. So x will be 2 meters. So how shall I place now the load for getting maximum bending moment at section C? So while it travels, okay, so at what position of this load the bending moment at C will be maximum? So it will have the location C will have various bending moment values as the load travels like this. So for each position that you imagine, like you are clicking a photograph of it. Okay, so for each position of load the bending moment will be there at C. So among all those values, which is maximum? Okay, so this position will give you the maximum bending moment. Now you see I'll place the load for the calculated position. You see x shall be 2 meters, which means I'll have to place the load like this, 2 meters to the left and 4 meters to the right. This is 2 meters, this is 4 meters. Okay, so total 6 meters is divided into two spans like this. Okay, and the load value is given as 10 kilonewton per meter. So this is the position of the load that you have to place for getting maximum bending moment. Now you just drop these end points of the loads onto the ILD, and this area occupied by the UDL, okay, multiplied by the load value will give you maximum bending moment value. So maximum bending moment at this section is equal to, let us say this is area 1, this area 2, okay, divided by this highest ordinate. So I shall calculate A1 plus A2 total area multiplied by the load value. This will give me the maximum bending moment. Okay, so let us calculate A1 value. So for A1 to get, let me call this as D, call this as E, the ends of the loads. So I call this ordinate as YD and this ordinate as YE. Okay, this height of this ordinate here, height of this ordinate, and YC value, maximum ordinate of the ILD, is simply the left span multiplied by the right span divided by the total span. So this is nothing but the 20 by 3 is the value, or else 6.667 is the value. Now from similar triangles, say this triangle is, this is total 10 meters, whereas the smaller triangle here that formed with YD, so 2 meters is to be deducted from 10, so it will be 8 meters. So for 8 meters, what is the ordinate? So that will give you YD value. It is simply 8 by 10 into the 6.667, that is YC ordinate, will give you 5.333 is the value. Okay, so let me come down a bit. I need YE value also. So you can see this total span is 20 meters. Okay, whereas 4 meters is the load occupied. So it will be 16 meters is the remaining span. So it is 16 by 20 multiplied by 6.667. Again by similar triangles only. The triangle formed with YC and triangle formed with YE. Have to consider both. So it will be working out with the same height. Okay, so it will works out to be same height, 5.33. Now A1 value, I'll just calculate A1 value here. A1 is, it's a trapezoid, you see it here. So it will be average of YC plus YD. That means 6.667 plus 5.333 by 2 average multiplied by the distance between these two parallel sides is 2 meters. Similarly A2, average of these two parallel sides is again a trapezoid. So it is 6.667 plus 5.333 by 2 average, and the distance between these two parallel sides is 4 meters. Okay, so both A1 and A2 values, if you work out, so A1 works out to be 12 and A2 works out to be 24. So put together, A1 plus A2 value is 36. Now what we want is maximum bending moment at C, that is equal to 36 into 10, which is 360 kilonewton meter. Okay, so this is the maximum possible bending moment when this UDL is traveling from left to right at this location C. This is the maximum possible bending moment. For all other positions except this position, like 2 meters to the left of the section, 4 meters to the right of the section, except this position, for all other positions the bending moment at C will be lesser than this 360 kilonewton meter. That's the meaning of it, right? Thank you.